and I'm working at the JCNS, and the JCNS is a Jülich Center for Neutron Science. It's actually a very experimental type of institute because the reactor is closed in Jülich since 2006, and so we are the first and probably the only delocalized neutron center in the world. We operate instruments in Grenoble, in Munich, at the SNS, and also soon, as soon as the reactor runs, in China. So, without much more, I will now come to the rapid description of the Mössbauer effect. Just remember, Mössbauer got a Nobel Prize for his work during his PhD, and actually it's nuclear physics he was doing. And what's fantastic is how nuclear physics led to this wonderful probe for solid state physics. And so the Mössbauer effect is essentially the recoil-free absorption or emission of gamma radiation. So imagine you are standing as a goal on a soccer field and somebody comes and shoots very hard. You need to catch that ball, and you will recoil always. Right? If you're not bound to the ground, then you enter in the goal with the ball. So fortunately in solids, the atoms are anchored to their neighbors. And so there is a probability that they can absorb this gamma radiation that comes without recoil. And so that's the Mössbauer effect. And the probability of the effect is very easily directly related to the atomic displacement parameters. So that's the probability or the Mössbauer factor. And now, because there is no recoil, the lines that you get in the absorption depend only on the lifetime of the nucleus. And for some nuclei, like iron, these lines are extremely sharp. And now you can do hyperfine spectroscopy, much like NMR does. Although we're working at very high energy, kilo electron volt, we get resolutions at the nano electron volt range. So, applications are very broad. They go from fundamental physics. Here I put one of the things, which is general relativity. Mössbauer effect was the first experimental proof of general relativity. And this one is a Mössbauer spectrometer. There is actually two, which are working on Mars. That's the first Mössbauer spectrum that was measured on Mars. And because we're at the battery conference, and I heard the talk from Rashid Yazani, he was involved in this project, there is of course also batteries in there. And it's still sending data now after 10 years of operation. So, thanks to Dr. Mahmoud here, I don't have to say much about isomer shift. The isomer shift is related to the shift of the nuclear levels as soon as you give it electrons. So there is a nucleus, and it sees electrons, so the energies are shifting. But the shift can be different in your source for the excited and ground state and in the absorber. And so when you Doppler shift your source relative to the absorber, you will see a difference relative to zero for the absorption. Here is a scale for iron. We saw the same for antimony. And in iron, it's not as clear as antimony, actually. There is things that are very clear. Iron 2 plus high spin, very clear in this range. Iron 6, iron 5 are usually easy to distinguish. But whenever you are in this region, you should be very careful. Isomer shift is not enough. You should do other things. Sometimes you can use the quadrupole interaction, which essentially tells you that if the environment for the nucleus is not symmetric, so you have positive charges here, negative charges there, because the nucleus has a shape, it can be elongated or flat, you will be sensitive to this. This would be a positive quadrupole interaction, and this would be a negative quadrupole interaction. Okay. And so you can use both isomer shift quadrupole interactions to learn about what your nucleus is feeling. And there is two contributions: lattice contribution, that's point symmetry, and then whenever you have iron 2 plus, be careful, because you have also valence electron contributions from the crystal field and orbital terms. And then finally, although it's not directly relevant to batteries, you have magnetic interaction, which give rise to the Zeeman splitting, and then you will get a sextet for iron, six lines, and the characteristic quantity is a hyperfine magnetic field. It's actually very important because sometimes isomer shift is not enough, and only the magnetic field can tell you what you have as oxidation state. So, as I said, the probability is the Mössbauer factor. It's directly the atomic displacement parameter. So it's exponential atomic displacement parameter and then some nuclear parameters. And it quantifies essentially the recoilless fraction, the zero phonon probability. What I should say about that is, if the Mössbauer effect is zero phonon probability, there must be something else, and I'll show one example later, which is the 1, 2, 3, 4 phonon probabilities. And so you see we are probing lattice dynamics, and you can do phonon spectroscopy with this effect as well. Okay? So, now we come to some applications. I will not go too much to the electrochemical details, but more show how we use this technique and what we learn about it. And so in this case, it was work done at the University of Liège, and the student tried to synthesize sodium iron phosphate with fluorine with carbon powders by spray drying in order to upscale the synthesis for industrial processes. And so the electrochemical properties are known. The recipes here, she used iron citrate, which also will give the carbon after you anneal the material, and then these ingredients, final iron concentration in solution was this, and then you have to find the correct parameters for the spray drying, the feed rate, inlet temperature, and then you need to know about the annealing. I will show only one list of spectra, which is here as function of the annealing temperature, but basically the student had the Mössbauer lab there, the spray dryer here, she varies the parameters, she goes, and while she prepares the next spray drying, she gets the result, and she knows, oh, I have iron 3, so something's wrong, let's change it. So she was really going back and forth. Here a bit about the microstructure. Before annealing, the particles look like this, that's 10 micrometers, and after annealing, they look like this. Very thin shells are forming here, and there's particles inside. And so as you see from the Mössbauer spectrum, when you anneal at 600 C, there is only a very little bit of iron 3+, and as you anneal higher, iron 3+ grows, and then some other phases come up, which I have detailed a bit here. So if you anneal too high, you start to form iron 3, then you have to start to form carbides, and at some point at 660 you even start to form metallic iron. So here a bit about the electrochemistry for the final material. The theoretical capacity that's a bit hidden here is 135 mAh per gram. And with this material, at very low rates, you get about 80% of that, and it's reduced a bit when you go at, let's see, here. So if you are interested in details, everything's published. Now, we have been working also with people from Stockholm University. They are interested in synthesis of some Rudolfson-Papper phases for solid oxide fuel cell cathodes. And in particular the N=2 material, which has strontium, rare earths, iron, nickel, and then deficient oxygen occupancy here. And the rare earths is yttrium or praseodymium. And essentially we have looked how this material evolves as you dope the trivalent cation on the strontium side, and what we can say about annealing in air with the oxygen. So the materials are interesting because they have good, not excellent, but good conductivity for oxygen, and they have quite low thermal expansion, which is the main difference. And so in these phases, when you start to play with oxygen deficiencies, there is a lot of different environments that you can have. And so here is one case where you should use low temperature Mössbauer spectra with magnetism in there, if the material gets magnetic, of course. Because when a Mössbauer spectroscopist shows you this and tells you, oh, here is iron 5, iron 4, iron 3, just don't believe it. Because we don't know, right? Everything is overlapping. Then you go down at low temperature, 25 Kelvin and 7 Kelvin, and you see it's splitting up with the Zeeman interaction. And as you can see here, each of these things corresponds to different fields, and when you combine now the hyperfine field and the isomer shift, for example the purple one here, it has a slightly smaller hyperfine field, but it's shifted also to the right, then you can attribute this to iron 5. And in particular, if you can consistently fit all spectra from low temperature to high temperature with one model, you know that you're on track. So here we looked at two things. What happens when you take this family and you substitute strontium with these trivalent cations? There is two things that can happen. One thing is that you could have iron reduction, right? The other thing is that you could increase the amount of the oxygen, so delta gets smaller. And so using Mössbauer spectroscopy and doing all the spectra as function of temperature for all these different compositions, here is for the pure strontium, that's for the one which is highlighted here, you start to get a feeling of the occupancies, and so here it's only iron 3 when you prepare the material under nitrogen, and you have iron 3 in tetrahedral and 2 pentahedral sites, and when you go to 0.4 praseodymium in performance unit, then you come to 100 iron 3 on a pentahedral site, but there is no iron 2 or other oxidation states. So basically you are increasing the amount of the oxygen, so indirectly we are sensing this. In contrast, if you prepare these materials and anneal them under air, what happens then is that the pristine material starts with having iron 5+ and iron 3+. And as you go to more trivalent cations here, what happens is that you're actually reducing your iron 5 and iron 4 to iron 3. And so this material here has iron 5 and iron 3, this material has iron 4 and iron 3. And now, if you do the whole series, you can plug everything together and try to see how the oxygen content evolves as a function of the substitution of the trivalent cation. So here are isovalent lines, so that's the oxygen content if you had only iron 3 and nickel 2+, and the only thing that you change is the trivalent cation. You would follow this. What we know from the Musbar spectroscopy, assuming there is only nickel 3+, strontium 2, and then the yttrium and praseodymium 3+, and assuming oxygen 2-, which is not always the case, but here it is, we come to the data points here in blue for the oxygen content. And then you can compare this with data that you get from X-ray diffraction or neutron powder diffraction, where you very nicely see the oxygen. And here we can get the occupancy of this O1 site, which is empty in the as-prepared phase, but it starts to fill if you anneal in air. And so you see there is quite a consistency here in this data in order to obtain the delta. Now I will talk very briefly, because we have seen other examples during the workshop here. There is one thing which is very nice for electrochemistry, is that you can do operando studies for the electrochemical reaction. And so this is a cell which is developed in particular first by Jülich, and now it has evolved in Montpellier. I have to acknowledge Hermann here, who gave me also the data and all these nice pictures. And so what they did is they used this teverite material, and so they cycled here, making a first charge. This charge is the electrochemistry, but in parallel they can do X-ray diffraction in operando, and also the Musbar spectroscopy, which then tells you at the microscopic level how the oxidation state of the iron, which here is the electrochemically active material, happens, and how you then come back. And you realize that here you don't come back exactly to 1 lithium, and that's attributed to some iron 3 which is stuck in the structure. Okay, so if you want more details, you can look, for example, at this publication. So, solid oxide fuel cells are probably known here to this community. So I use air to provide oxygen, I use hydrogen, any type of source, could be hydrogen or methanol, and I have a reaction here, you have an oxygen conductor, and then I can generate electric current. That's using this as a solid oxide fuel cells. We have colleagues in Jülich, in the Institute for Energy and Climate #1, which reverse the process. They are interested in the other way around. Suppose you have too much electricity, maybe at noon in Morocco, then you can try to take a solid oxide fuel cell and make a solid oxide electrolysis cell. And you run it the other way around. So you have water, you feed water in, you have air, you feed air in, you get more oxygen out, and you get hydrogen, which you can store. And so they were interested in this anode material, which is lanthanum, strontium, cobalt, iron oxide, and how it behaves in terms of long-term stability. And so for that also, Musbar spectroscopy is extremely sensitive to also small changes and small amounts in the long-term aging process. So this is material which is pristine. Then you have the iron 3, and iron 4 occupations for the various sites. We did, of course, the low temperature measurements. So don't believe that, believe the low temperature measurements, which I will show in a moment. And then we received the material after 1,500, 6,000 and 9,000 hours of operation in the cell. And so the spectra here change a little bit when you go to the low temperature spectra. You have a bit more details, so you can attribute the size. And essentially you see that there is a little bit of iron 4 plus vanishing. And I don't have any data on the capability of the material after 9,000 hours, but it's not degrading very much, and that's in line with what we see. So, I switch gears. Musbar spectroscopy, one thing, and then in the 70s somebody in Argonne had a very good idea. He said, well, why do I need a radioactive source? I have a synchrotron. I can pump these levels with synchrotron radiation. So that was 1974. He spent all Argonne travel budget going to the synchrotron, which was not in Argonne, it was in California. Tried to find the effect, and he didn't find it. It's very difficult when you don't know what you're looking for exactly. So the effect was discovered in 1985 in Hamburg, in Germany, and since then, in 30 years, this technique has evolved tremendously. And so now you can do many things. You take a synchrotron, ESRF or one of these three. You use monochromator. Typically, you reduce the bandwidth to keep only photons around in nuclear resonance with millivolt resolution. And then you can get time domain mass spectroscopy. If you use a nuclear monochromator, which is a new development, you can get energy domain mass spectroscopy. Why would you do that? You can do it in a lab. Well, now you have a microfocus beam. You can look at thin films. You can look at high pressure, very tiny samples, and so that's why you would do that. And here comes what I mentioned. If there is zero phonon probability for Lamp-Mössbauer effect, all the rest is nuclear absorption, which is phonon assisted. And so when you look around the Mössbauer line, which is here, and you scan with millivolt resolution, you start to see all the phonons where the iron, in this case, is involved. And so you have a phonon spectroscopy method. That's an inelastic scattering on iron, and that's the phonon density of states of iron, which you can measure in this way. What can you do? Well, everything that has a color except this color is a Mössbauer active element. So basically, once you are here, almost every element is Mössbauer active. Until there, only a few are. And from these elements, some of them, in particular those in pale blue here, are very difficult in the lab because there is no good sources. And here I highlighted in black and in white, and with these arrows, what you can do at the synchrotron. So black and white, it means you can do Mössbauer spectroscopy and phonons, and with these arrows, it means you can only do Mössbauer type measurements. But you can do iron, nickel, ruthenium, as I will show, germanium, for example, even though it's a bit involved. What's limiting actually is that the lifetime of the Mössbauer nuclei, when it gets very small, puts a strain on your detectors. They have to be very fast. And the transition energy, as it goes up, you need to have more photons in the beam, and you need to have more efficient detectors to see these photons. So, one example here, which comes, it's a byproduct from thermoelectric research. The people were interested in nano-antimonides for thermoelectric applications. And so it's a wet chemistry preparation where you start with some iron salts. And you put this in solution, you add iron antimony nanoparticles, you heat to the correct temperature, and then you wash out, and you obtain many of these antimonides, zinc antimonide, nickel antimonide, and then iron antimonide. And here we use a technique because at some point diffraction fails. It's nanomaterial, so the peaks are broad or non-existing. And then you can do something using nuclear resonance scattering, which is actually very close to Raman spectroscopy. We used the vibrational spectrum here to say, well, look, that's the bulk, and that's the nanomaterial. There is no signature of any antimony impurity, so that's fine. So you can use that for purity assessment, and what we found out is for thermoelectrics is that this reduced speed of sound in these materials. So now maybe just one slide to show you what does a synchrotron do in a different way than Mössbauer spectroscopy. We come with a pulse beam, we excite nuclear states, that happens at t equals 0. Then for some time we have to switch off the detector electronically. And then all these nuclei that are excited will decay. And they decay in a coherent way and emit this signal. And you record it as function of time. It's close, but not exactly, a Fourier transformation of the Mössbauer spectrum. And so that would be the Mössbauer spectrum equivalent to this. And this was done for tellurium-125. Which is nowadays a bit difficult because you cannot get hands on a source. So you can do it at the synchrotron now. Alright, so what did we do else? It's essentially part of method development. This was a very challenging isotope which sits at 70 keV, so you need a third generation synchrotron. And we did 73 germanium Mössbauer spectroscopy with this level. With that you can obtain, if you're interested in lattice dynamics, the Lamp-Mössbauer factor, which gives you the Debye temperatures and germanium oxide rutile or quartz structure. The rutile structure is much harder, for example, than the quartz structure. And you can also get the oxidation state. So now, because you have no source, there is no reference. And whenever you want an oxidation state at the synchrotron, you need to put two samples and get the shift of one relative to the other. Which we did here for germanium oxide relative to germanium sulfide. That's a sulfide alone, and that's the oxide in rutile and oxide in quartz phase against sulfide, and then you can construct a table of isomer shifts for germanium. Actually, with this one experiment, we summed up as many samples as existed total in the literature before we started, because it's extremely difficult in the lab. So, ruthenium is most reactive. So why would you do ruthenium? We had a good incentive to do ruthenium yesterday because there's the nice ruthenium nitrides, and what we found before doing ruthenium is that there is this paper here where we're interested in lithium insertion in the ruthenium dioxide in the rutile phase. And so we didn't do these materials yet. That might come. But what we did is we showed that you can do ruthenium most-power spectroscopy at the synchrotron, although it's very high energy now. It's really at the limit of what's feasible. And that's spectra on ruthenium dioxide that we acquired at different temperatures, as usual, to assess the most-power factor. And so in principle, nothing is in the way to look at oxidation states of ruthenium using these techniques. And it can be done in principle in situ because you have a very small beam and you can probe thin films or small amount of materials. So, I look at time, yeah, I look fine.
Also I look at time.
Yeah, it's fine, so I have time for neutron scattering here. And the colleagues in Institute for Energy and Climate, they're interested in electrolytes for oxygen, and so they use this Nasicon type structure, lithium aluminium titanium phosphate. That's also for solid oxide fuel cells. And there were some structural problems. First of all, there is some high temperature transition. They do not understand, not yet. We have more neutron data coming on that. And they wanted first to get a room temperature structure, a correct structure where you see the lithium. And that's where neutrons are good. They're good at seeing light elements like hydrogen and lithium. And here we use the spallation neutron source in Oak Ridge, where we operate part of the beamline. And you have this extremely resolved time-of-flight neutron diffraction spectrum. You cannot do this with X-rays because it would correspond to going to 720 degree to theta, which you cannot do. Okay? Or you would go to high energy and then you don't have resolution. And so they found that they have a very small impurity here, which is a secondary phase. They refined the lithium in the structure on the 6B side, that's known, and they found, oh, there is a little bit of additional lithium in the channels on the 6A side, which was never described so far. So here is where neutrons, which is another nuclear technique, actually it's probing only nuclei, comes into play. And then I come to some final example. I'm absolutely not involved in that, but this study is so beautiful that it should be shown more. And so the people in Rennes, under Werner Paulus, who is now incidentally in Montpellier, were interested in ionic mobility in electrolytes for fuel cells. And so the limiting parameters for the oxygen diffusion is essentially concentration of vacancies, barrier heights, and the size of this huge anion, which is oxygen. And so there is many intercalation structures where you would like to understand this oxygen transport. In particular, they were interested in the brown millerite, strontium iron O2.5, and one fundamental question: why can I not electrochemically fill the brown millerite to perovskite in the calcium iron O3, but I can do it in the strontium? Why? What's the reason? And so what they did ab initio calculations, and they did neutron scattering, inelastic neutron scattering. In a neutron scattering in the strontium system, you see here there is a low energy phonon mode at 7 millielectron volt, and that mode is actually at 12 millielectron volt in the calcium system. And when you heat the calcium system up, this mode starts to soften. And so what they also did from ab initio calculations is that they looked at the lattice parameters and at structural instabilities. And actually, in the strontium system, the B lattice parameter is quite large, which brings you this soft phonon mode, a small structural distortion. Whereas in the calcium system, you are here, and this soft mode does not exist. But when you heat the calcium system, you reach this critical value of B, and the system gets soft. So now, let's have a look at the details about the neutron scattering. Here is your Bragg peaks. When you do diffraction, that's that. It goes somewhere to the moon, lots of intensity, and here are the phonon modes. So in the strontium system, you see this soft phonon mode here. And if you look a bit more carefully, you see this diffusion intensity here, scattering intensity, is connected to the soft mode, and you see a quasi-elastic contribution, which tells you, oh, that's not atoms vibrating, that's actually atoms diffusing. And they diffuse assisted by this phonon here. In a calcium system, even at 1000 Kelvin, there is no quasi-elastic scattering. So that phonon is just too hard. It's not yet populated enough to help the oxygen in the diffusion. You can do molecular dynamics and you see that indeed that's the case. The calcium system, the oxygen stays put on site. In the quantum system, it starts to diffuse here in between. And so you have an oxygen that goes from here, then here, and then there. And so here the oxygen diffusion pathways are clarified by this. And why it's working actually with iron is because iron has this large flexibility in valence states and configurations. So you can go from SrFeO2, although that's very unstable, all the way to the perovskite with all these oxidation states. And so these soft phonon modes I think are quite promising. You have to look for that if you want high diffusion. As a conclusion, mass spectroscopy spectroscopy, well, you can use it for many things. Whenever you can do it. It's cheap and it's very informative. You can do screening, primary characterization, detailed structural studies over oxidation states, in situ operando or ex situ studies for electrochemical processes for aging. You can use synchrotron radiation whenever you need vibrational spectroscopy for one particular element, if you have thin films, or if you have a difficult isotope where there is no source. And then neutron scattering is recommended whenever you want to visualize the light elements, or if you need inelastic or quasi-elastic contribution. So, with that, I need to acknowledge many people, in particular the German Research Foundation, all the colleagues that have here, and the team. So, all in particular, Benedikt Klobes, Mahmoud, Rami Simon, Elias Sergeyev, Dimitri Bessas, and Tanya Clary. And I thank you for your attention.
Okay, thank you.